pleasure of welcoming Stefano Olla, who's going to talk to us about how to get the heat equation from a deterministic dynamics.
Okay, thank you, Clement. Thank you to give me this occasion to talk at IMPA and in South America. I miss a lot Rio de Janeiro. I'm happy to be there, at least virtually there. I mean, now it's more than 4 years I'm not coming. Hope there will be occasion in the future. I miss you guys. But so what I will talk is something that we worked on this last year in collaboration with Carlangelo, Liverani, and Giovanni Canestrari. I learned a lot about dynamical systems, things that I didn't know. And basically, thanks to techniques that Carlangelo did push up on studying fast, low dynamical system, that one can avoid this problem. Okay, let me say, for many people, I mean, Milton already heard this. I'm sorry if I would bother you with that, but I don't assume that everybody is familiar with the hydrodynamic limit and with deduction of heat equation from microscopic dynamics under diffusive time scaling. So this is the heat equation, the nonlinear heat equation. The K is the thermal diffusivity, C is the specific heat, and T is a temperature that evolves in time and in space. And maybe it's better to write it in terms of the conservation law for the energy. Energy and temperature not necessarily the same thing, as you know, but in the case we will study later, they will be the same thing. And there's a usual connection that there is between the diffusivity of the energy and the temperature of the temperature. And the point is how to obtain this equation from a diffusive rescaling of space and time from a macroscopic dynamics, possibly the Hamilton equation. Of course, this is a kind of a dream for mathematicians, so it's not even clear under which condition this will be true, and it's not always true. So we shall try to make things as concrete as possible. Let's take a chain of oscillators. V is the interaction, so there are oscillators at position Q and velocity P. Let's take mass equal to 1, so velocity P is equal to momentum P. So there is a connection between the particles. Do you see my? Yes, you see the red thing. Do you see the red spot?
Yeah, we can see the dot.
Okay, so this spring could be something nonlinear regulated by this potential V, depends on the distance between the particle. Then there is a pinning potential, let's call it W. And there is a kinetic energy, which is P squared over 2. So this will be the total energy of the system. And we assume that we just denote E of X, whatever inside here is the energy of a single particle X. We attribute to the particle X the potential energy of the spring to its right. And this is the energy is conserved under Hamiltonian dynamics. So the energy of the atom X, there will be some flow of energy, some current of energy going from X minus 1 to X, and some energy going from X to X plus 1. And this is the time derivative of the energy. This is because it's the energy is conserved. So basically, already on the microscopic level, you have one gradient, and the whole mystery is to get the second derivative. How does it appear? The current can be written explicit. If you do the calculation, it's just minus px, the derivative of v between the particles. You see, in the current does not appear the potential, the pinning potential W. These are the energy current. Okay.
Stefano?
So, yes.
Do you consider some specific boundary condition, or is it free?
Okay, no, we will take periodic boundary condition. I will specify later. At the moment, I'm just talking generality. Anyway, don't worry. For the nonlinear case, I cannot prove anything, of course. So the point is just think about periodic boundary condition. These are a system of length n, and there is some period. I will specify that later better. And what we are looking for is a limit of this kind. We rescale space and time. There's a parameter epsilon that rescale space and time. Eventually, we'll take epsilon, the total. If we find volume, the total epsilon minus 1 will be the total dimension of the system, of the total particle, or the total number of particles. And rescaling diffusively space and time, we should get a distribution of the energy that satisfy the diffusive equation, the heat equation. The connection that you expect between the microscopic dynamics and the diffusivity, the thermal diffusivity D of E, is given by the Green-Kubo formula, which is this formula here. So you see the Green-Kubo formula is a double integral in space and in time of the space-time correlation of the current, with some factor that depends on the temperature that corresponds to the energy E in equilibrium. So you can recognize here this variance as a probabilist, and it's important to recognize later. The diffusivity is a space-time variance of the current in a space-time central limit theorem. This expectation here is the equilibrium dynamics. This correlation is taken in the equilibrium dynamics at energy E. There will be an equilibrium measure given by Gibbs measure, which connects the temperature and the energy. And so there's the dynamics in equilibrium. This will be for the infinite dynamics. So sum over X is over infinite space. And you can prove that there is this dynamics in equilibrium exist. And it goes, but already the proof of the convergence of such double integral is an open problem if you take just a purely deterministic dynamics. Is in general, even not only this problem is difficult and unsolved, but even the existence of the diffusivity is an open problem, except in very particular case. So that's what I said. Even the convergence of the Green-Kubo formula for this is not proven. Most of my life, I worked taking Hamiltonian dynamics and adding energy-conserving noise to try to prove hydrodynamic limits. So if you add some energy-conserving noise to the dynamics, we'll say random flip of sign of the velocity, one can prove that the Green-Kubo formula converge. For example, you just at each particle, you say, okay, beside the Hamiltonian dynamics, you wait an exponential time and you flip the sign of the velocity. This, of course, kills a lot of integrability of the system and makes that integral convergent. And I made a work with Cédric Bernardin maybe 15 years ago, or more, little less, where we proved that. In general case. For diffusive problems that are not the energy, you have a technique which is based on relative entropy production, that with what you can prove hydrodynamic limits for stochastic dynamics. This is the line that started with Vardan and Yao, and I've been working, and many people there, Claudio, many people worked on this line. Always with noise inside the system. These relative entropy techniques, though, do not work for the energy. When you want to study hydrodynamic limits for the energy, the entropy is useless. The reason is that the entropy does not control the energy. You get entropy bounds, and these entropy bounds are useless to control the evolution of the energy in the hydrodynamic limit. I'm not going inside that. But for harmonic chains, where you take V and W quadratic, so V and W quadratic, the dynamics will be linear, and we put only noise that conserve energy, then it's possible to prove heat equation in the diffusive limit, at least in the average, not as a low large number, but at least in the average sense, the average of the energy. after diffusive limit will converge. Actually, amazingly, this is the proof of this is only very recent, the paper with Tomasz Komorowski and Joe Leibowitz that has been published last year in Communication Mathematical Physics and in GSP. Okay, so what I'm interested in, and I've been discussing with Carlangelo about this for maybe 30 years, not exaggerating, we are old, is about how to use, instead of stochastic dynamics, instead of stochastic perturbation, deterministic perturbation that are chaotic. So that you have deterministic evolution, chaotic but deterministic, and somehow the deterministic chaotic part plays the role. We substitute the noise. I can see this as an academic question, or other people can see this, well, you can actually prove diffusive equation, which is something really related to stochasticity, from a completely deterministic dynamics without putting any noise in the dynamics. The only noise should come from the initial condition. So, and this is what we have been studying. So we have the Hamiltonian dynamics in black, linear. So there is a pinning potential with strength omega 0 square is the strength of the pinning potential. This Laplacian represents the interaction, the harmonic interaction with the nearest neighbor. This Laplacian is a discrete Laplacian over X. So this will be just the linear dynamics, which will not have hydrodynamically, will not have heat equation, because the deterministic dynamics without anything else is completely integrable as infinite many conserved quantities. Is one of the trivial situation where you don't have a closed equation for the macroscopic evolution. We'll get more into it's a very simple elementary example of the generalized hydrodynamics of completely extended, completely integrable system. It would be just a trivial case. But we are not there because we perturb the system, the dynamics, with a deterministic dynamics, chaotic. So F is a map, is a chaotic map. Let's say theta is an angle. Theta could be 1 or 2 dimensional on a torus or on a circle. We'll specify later. There is a map, which is a chaotic map. It's speed up by a parameter epsilon minus epsilon. So this is acting fast respect to the movement of the atoms. And there is a scaling parameter, should be epsilon minus 1/2. And B as a null average respect to the invariant measure of this chaotic dynamics F.
Stefano?
J, yes.
Can I interrupt you with maybe a silly question? It's because it's actually opposite of what you're doing here. But so if you start with an integrable system and you perturb it with something which is not very big, I think CAM theory tells you something about the new dynamics, right? That is not very different.
We didn't study this, but I'm sure that with this perturbation, the complete integrability is broken.
Okay.
Yeah, it's certainly, and in fact, otherwise we will not have a macroscopic equation. But we didn't actually prove this. But I think one sit down can actually prove it that the complete integrability is broken in some sense. J is this matrix here. This means that the effect of this noise is to rotate. Sorry, very important. Qx and px are now in 2 dimensions. Okay. So there are 2 components. For each atom has 2 degrees of freedom. So velocity is just as 2 degrees of freedom. And I'm rotating within this degree of freedom in a deterministic chaotic way. But this is a rotation. This is a rotation of the velocity. But the modulus square of the velocity is conserved. So the kinetic energy is conserved. So this dynamics conserve the energy of each particle, the conserve the kinetic energy of each particle, so the total dynamics conserve the total energy, because the total energy was already conserved by the Hamiltonian part. Okay, so the point is that you have to accelerate these dynamics very fast. I say, okay, just as fast as we can, as fast as we need, not possibly not too fast, but as fast as we need. And it turns out that we have to accelerate. If n is the number of particles, here there are n particles with periodic boundary condition. If n is the number of particles, we have to speed up like n to the minus a, with a bigger than 6. If you work better, you can get better, but with this technique, you have to speed up. Will be nice just not to speed up chaotic dynamics and let the dynamic limit, this diffusive speeding up of the dynamic limit should be enough, but this will be a much harder problem. This is what we can solve. So let me tell you something more about this map F. You see, this is the integer part of T minus 1 because the map is a map that jumps at deterministic time. And there are two possible cases. The easy case, you take a smooth map on the interval from the torus to the torus. For example, you double x to 2x. This is the clearly case. The derivative will be bounded by a parameter lambda bigger than 1. In that case, lambda is equal to, so it would be bigger than 1. And there exists, you know that the standard theory of dynamical system tells you that there exists a unique, absolutely continuous invariant measure. You call it rho star theta d theta. And you can also prove that there's an exponential decay of correlations. So the people in dynamical system know a lot about this. Another case which will be more interesting, in fact, which is more interesting, in fact, is the Aharonov map on the torus. And then theta has two components in the torus, theta 1, theta 2, and the map, for example, does the mix up. It's like the cut map. The advantage of the Aharonov map on the torus that is also time reversible. So that means that we are putting a perturbation of the Hamiltonian dynamics that is deterministic and time reversible. Time reversible in the sense of dynamical system. The smooth map on the interval is not time reversible, deterministic but not time reversible. Just, I mean, to deal with the Aharonov map is a bit more complicated because you have to deal with direction which are stable and unstable, but the effect is this, in terms of the hydrodynamic limit will be the same. Same thing here. It's well known from the theory of dynamical system that there is a unique invariant measure. We denote this always with rho star, is absolutely continuous respect to the Lebesgue measure on the torus, and you have exponential decay of correlation. Okay, so these are the type of chaotic deterministic perturbation we put in the dynamics. So I write here the dynamics. So now you know what is f of theta x. And every time this jumps, there's a rotation that is happening. So the average of B, we take it equal to 0. This is not really necessary, but this is just, we have to recenter, otherwise there's no particular thing, but it's quite natural to take the average of B is equal to 0. And one of the things is important to avoid a trivial variance is that there exists a periodic orbit such that the sum of B over the periodic orbit has to be different from 0. This guarantees that this quantity gamma is positive. This is the variance of the central limit theorem for this function B under this dynamical system. So that means if I take B, fk theta, and sum over k divided by 1 over the square root of n, this converts to a Gaussian random variable with variance gamma, and gamma is this. This condition of the existence of this periodic orbit is a condition that guarantees that this gamma is strictly positive. Of course, you have also invariance principle that you can prove that this converges to Wiener process. And okay, so this is goes into the standard theory of dynamical system. People in dynamical system, and there at IMPA you have very good ones. They say there's no problem with that. And these are the Wiener. So when you accelerate, this B seems to have effect of a Brownian motion. So it's like putting some randomness. But in principle seems obvious, but when you go to there to do it, it doesn't look so obvious. So now we are working on a completely dynamical system. So if there should be some noise coming in, otherwise it will not be diffusive equation. And this noise comes from the initial distribution. Let me sorry. The initial configuration are the configuration of the particle, the configuration of the velocities, P, and you have also to give initial condition on this angle theta, that the starting point for all this dynamical system. Each atom has its dynamical system, and then there are these maps, and then you have to give this initial dynamical system. So the initial distribution should be a distribution on Q, P, and theta, and is a probability measure on Rn times Rn. It should be the same Rn, and the torus theta n, and for each angle there is a torus. And we ask that on the distribution of the velocity and the position, we don't ask much. This could be anything, even deterministic. What is important is that the distribution of the angle are absolutely continuous. So there is some initial randomness in this angle. That's what you have to work on. That's where it comes from. The initial distribution will be a product of some rho x, and you need a technical condition that these densities rho x have to be somehow smooth. The logarithmic derivative have to be bounded. So this gives some smoothness. So it is important that there is a certain smoothness in the distribution of the angles. While the distribution of position and velocity conditioned on the angles could be absolute, could be even singular. It can even start with a deterministic configuration of position and velocities. The angles will do all the work. And then you also need to ask that you have initial profile for the energy. So you look at low large number, local low large number for the energy, and you have to converge in this sense to some initial profile E0y. E0y doesn't need to be really absolutely continuous, but let's take it absolutely continuous. And you have here you have just making local average with some test function phi in the circle. T is just the circle 0, 1. So we have the system of n particles, but now n particles is x divided by n. Here in the lattice is the lattice system. So phi x over n is between 0 and 1, and this is the low large number you look at. So now you consider the solution E of this diffusive equation with this initial profile. And we want to prove, and that's what we prove, is that in the expectation sense, if we speed up, if we look at the diffusive time scale, we converge to the solution of this diffusive equation. This will be where the diffusive coefficient d is d over gamma, where gamma is this variance that was appearing in the central limit theorem for the maps, and d is it is explicitly computable, and this quantity here depends on the pinning potential omega 0. You can see that when omega 0 goes to 0, converge to 1, which will be the case of unpinned case, which I don't want to discuss here because there will be more conserved quantities. Okay, so this is the theorem that we prove. As you see, it's not a low large number, it's in expectation. And the reason why is in expectation is what I said before. We have no control of higher moments than 2, unfortunately. if we even work with entropy, we will not give higher control of moments of order 3 or 4, and this doesn't allow to proceed to prove a real or large number in probability or almost surely. In probability will be the sense here, but we only have it in expectation. But this is what we can do. And for people that likes quantitative result, we can also estimate the distance between the empirical distribution of the energy at n fixed and the final result. This will depend on the smoothness of the function phi. And, remember, alpha, we take it bigger than 6. So this will give this how close we are to the final limit if we have n big. Okay, and that means that if we look at a larger time scale, let's say beyond the diffusive time scale, as beta positive, we converge to equilibrium. So we really get the global equilibrium. This is a system that you can start in non-equilibrium and is capable to arrive in this looking at very large time to a global equilibrium. This is interesting from thermodynamic point of view. This is the equation, and the point that this diffusive equation actually is the same diffusive equation that appears in the stochastic dynamics. The stochastic dynamics is this one. We have the same Hamiltonian dynamics here in black, and the stochastic terms are here. These are rotation. This looks like a Langevin. It's not a Langevin. This is really rotation of the velocity. Basically, each atom rotates the velocity, and is a Wiener process that on a circle that is rotating it. J is the same matrix as before, so this JP is the action of this rotation, and this is written in Ito way, which the way I like to do calculation. For people that are fond of Stratonovich form, the equation will be written this way. I'm not fond of Stratonovich form because I don't know how to do calculation in Stratonovich form, but these are absolutely equivalent. But in Stratonovich form, you can probably see more that this is the noise here is rotating randomly the vector of the velocity of each atom, and this is creating enough. Sorry, where am I? Yeah. Okay, and this stochastic dynamics has exactly the same macroscopic equation. If we choose gamma, the coupling with the noise, exactly the same as this at that variance, then we get exactly this, the gamma appears here, the gamma that is here. So if we just choose the same gamma coming from that variance, we have the same macroscopic equation. So intuitively, what you think is that the microscopic deterministic dynamics should be close to this stochastic dynamics. The stochastic dynamics at this dynamic limit, and so the deterministic one as a dynamic limit. You can actually prove, speeding up much more, that the stochastic dynamics, the deterministic dynamics converge to the stochastic one. But this is not our purpose. We want just to prove heat equation. And for doing this, we don't need to speed up so much. We don't need to show that the two dynamics are the same. It's enough to show that the evolution of the covariance will converge to the same evolution. Okay? And this is now, if you have a question about the statement of the problem and the result, is now the moment, because now otherwise I will start to talk about how we prove this this theorem. So the theorem we want to prove is this for the deterministic dynamics, for these dynamics here, and we know that will be the same as the one for the stochastic dynamics. So we want to show, in fact, that second moments are evolving the same way. That's really what we need to prove. So let's see how to. Is there a question at the moment? No. I don't hear questions. So let's see how to prove this. We look at the time evolution of the energy. We look at the time evolution of the energy in the diffusive time scale. So we compare the empirical distribution of time n squared t to the one that I had at time 0. And then I compute the time derivative. I know that E of x is conserved, so the time derivative, there is the discrete gradient. The discrete gradient, I can move it on the test function phi, so I have a phi prime here. And there's a little an error that eventually will be small, and this will be the main part of it. In this process, the speedy time is n square. When I compute the time derivative, I get an n square in front. One n square, I needed to reconstruct the space derivative of the function phi, and I lose the other 1 over n here. So I get the sum over x. This looks big, but fortunately, this time integral of the current is going to be small of the order 1 over n, and we have to determine exactly how much it is, and this will be the point. So we have to concentrate on what's happening to this time integral of the current. Now, if you remember the expression that I gave of the current at the beginning, the current is given by px, q times qx plus 1 minus qx. So you just separate with a minus sign. So you just separate the two terms. So this it's a matter to have information about the correlation between px and qx and px and qx plus 1 at the time ns square. Don't need to do that. We just need information about the time integral of that. And we want to prove that this is close to the same quantity of the stochastic dynamics. If we prove that, then we can proceed as we proceed in the stochastic dynamics. Okay, so how do we proceed in the stochastic dynamics? We write down the covariance matrix evolution. So let's look at the whole full matrix. Well, we are not really looking at the component. We wanted to, this is the dot, is a scalar product. So we have the covariance of the Qs, the covariance of the Ps, the covariance of the PQ, and the covariance of the P. So we have a big, now we have 2n by 2n matrix. And you look at the calculate, you put them in the equation, and you see that since you integrate in time, you get a relation over these quantities here, and there is a time, this is because you study with time derivatives of certain quantities, and there is n square, so when you divide by 1 over n square, you get some small terms here, I'll call them RNQ, RNQ, PQ, PQ, and so on. These are small, these are negligible matrix in some sense. You have to prove that they're negligible, but basically negligible because this is a result of the time integral of a very large time scale of a time derivative. So will be divided by n squared. In principle are small. So these are small quantities. Otherwise, you have all these relations between these matrices, and you sit down. These are linear relations. You put you work in Fourier coordinates, and you can diagonalize these things, and you can actually have information about that. And the information you get is that the current, this is the quality, this is what the current is. Jx is a difference between these elements of the matrix QP, is the matrix QP that matters here. And this is really what you get in the stochastic dynamics, is that solving those equations, you see that you get a second derivative, and you get the diagonal mat terms of the matrix of the P, which are P squared, plus something small. I'm not going to this. This is just linear algebra. In fact, you sit down. I mean, it's complicated. It takes a couple of pages, but it's basically linear algebra. And you saw this is for stochastic dynamics. This is for stochastic dynamics. And then you're almost there, but you don't have the energy. You have the kinetic energy here. You want to close this integral in the energy, not in the kinetic energy. So you still need to prove an equipartition of potential and kinetic energy, that this potential, this Px square is equal to the potential energy of Qx. So basically, equipartition means that kinetic energy and total energy should not be too different. And then you can conclude the equation proving this. And this requires another argument that can always solve it within the stochastic dynamics. So this is the proof how it goes for the stochastic dynamics, and I knew how to do it. And now, so how do you do it for the deterministic dynamics? Then let me go back still on the random evolution of stochastic dynamics. You have the stochastic dynamics as a generator, where there is an Hamiltonian part, A, and a random part. This is really this is the generator of the rotators, the rotation. You take the square and you get random rotation on a circle that rotates the velocity. So this is the generator of the random evolution. So for the random evolution, those equations for the covariance matrix are obtained just taking G applied to the function A, which will be part of one of these matrix, some quadratic function, which could be expressed in terms of the covariance, and integrated in time. So this is a time derivative in the case of the stochastic dynamics. So it's just, when integrate in time, it's just whatever you have at n t, n square t, a0 divided by n squared, and this is small. These are those matrices Rn, which I say they are small. No problem with the stochastic dynamics. In deterministic evolution, you want to prove the same thing with the same generator, but now that this is not the generator of the deterministic evolution. So you have to show that you get the same thing, but with a little error that depends on this epsilon n. And if you choose epsilon n fast enough, you have to show that this term is small. So it's really here that you have to play the thing. If you get that, then you get this equation for these quantities here, that is for the various choice of A, this will be small, and this gives you the same linear relation for the covariances that we found before. Okay, so how do you do this? This is the difficult part until, well, at least if you know how to do the stochastic part. For me, this was the difficult part where I have to learn new things. The natural idea that you have to do here is to split the macroscopic time interval, this is 0 n squared t, and you divide it in interval length h, time integral length h. This should be, h should be big enough so that the map is bring you close to the equilibrium distribution. And so the SLT variances are close to the equilibrium one, which are these gammas that we wrote before. But they should be short enough, this h, that the configuration of the particles, QP, move very, very little. So you have a needed tool to separate these two scales. So basically we have here three scales. We have the scale in which the very, very microscopic time scale in which the maps are moving. Then there is the scale where the particles are moving. In this scale, the maps are moving very fast. And then there is a macroscopic scale, which is the diffusive scale in which the energy will evolve eventually. So there are really three time scales that have to be connected to each other. There, because we only want to work with one parameter n. This is not a double limit. This is only one straight limit in n. So the main difficulty is that to prove that at each time step, so you do the step length h, you get a new distribution of the angle. We started with some distribution of the angle theta, and now we let it evolve. The theta evolves how they want, and then they move to a configuration, the QP moved a little bit. Now you have to show that condition to the position that you got, Q and P, the distribution of the angles are still some absolutely continuous part. There's still some enough smoothness so that you can restart the process. If you lose that, then you are stuck. You cannot use anymore the properties of the dynamical system. The dynamical system needs some initial smoothness. So you need the technique that shows that this initial smoothness you had at time 0, you still have after a time h, and you can iterate without losing anything. Without losing anything, everything has to be uniform in the parameter n. N is going to be big. And the mathematical tool to control this is called standard pairs. I don't know if there are people in dynamical people in the audience at IMPA. They certainly heard about that. This is basically a technique developed by Dimitri Dolgopiat, but the basic ideas go back to Ward of Sinai, of Lisa Young, and so on. And Carlangelo really developed this a lot. Intuitively, standard pairs are measured on the angles that are closer to a delta function, for which deterministic dynamics are still exhibit statistical properties. Okay, this now maybe this is slightly technical, the way this is constructed, the standard pair are constructed. Basically, there will be, for each angle, there will be an interval, let's say ax bx, small, which will be this eventually the support of each rho x, of each initial distribution of particles. Then there is a map that goes from this interval here to a configuration of particles. R2n by R2n are configuration of position and velocity of particles. So basically, to each theta, you assign a configuration of particle that you call g x of theta. And you call g, yes, these are for the particle x, and then you go from x to 1 to n, you get, so for each sequence of angles, theta 1, theta n, you have a configuration g of theta of particles. And these maps here, G, must have the property that the energy is constant. So you can change theta, but the total energy of the configuration that you obtain is a constant energy. It doesn't change if you change theta. The configuration G of theta must change little if theta change in this interval, and change little is in this sense here. This is it's kind of an infinite norm of the gradients. So you take gradient square, you sum over all y, and you take square. So it's L2 in y and kind of sup in x and theta. This has to be small in the sense there will be a bound on C bar. Square root that will depend on the total energy that we have fixed, and this epsilon. This epsilon that was a parameter that was in the map. Now it happens now it's not finished. To these maps GL that you construct this way, to the angles, to the configuration, you also put some distribution, some product distribution over the angles, which have support in these intervals. And they must have, important, this smoothness condition. I mean, in the C0 map, so that's a sup over that integral of rho prime x over rho x has to be bounded by constant. So they must have some smoothness. And the point, this is the miracle, which exists, I mean, that you worked out, it's just for the map F, is that there exists a constant C0 large enough such that this property is considered by the map F. So you apply map F to you pull up the distribution of rho x to the map F, you still have this property here. It's conserved. This thanks to the chaoticity, the fact that there is a spectral gap in this map, and basically I'm telling you now how this is proven, in fact, for the map on the interval. For Atonov map, the situation is slightly more complicated, but it works in a similar way. The standard map, so the standard pair is the couple of this function GL, which to the angle associate configuration, and to these probability densities, rho L. So depends on all these parameters. There is n, the number of particles, there is total energy, there is delta, the support of the maximum support of the intervals, there is the parameter epsilon, C bar, C0, there are all these maps here. And a map standard pair induces a probability measure on the configuration theta qp. So you take a function of theta qp, which is a configuration of the particle. There are the angles, there are positions, there are velocities. And you define a probability measure in this way. You integrate over the angles, and the position you computed as a function of the angle. Okay, this is a standard pair. This is a probability measure on a particular construction of probability, initial probability measure. And this is a fact, this important fact that you have to prove is that if you let it evolve now with the dynamics, the standard, you start with a standard pair. You can start with one nice standard pair. What you get at time h is not a standard pair, but it's still a convex combination of standard pairs with the same parameters. You're not losing anything. It's not just a single standard pair, but you have the same parameters. So you can actually restart things. So this allows for a proper choice of the parameter of this time step h to control the error in the calculation of the covariances uniformly in n. You have to choose epsilon small enough so that to speed up, that means you have to speed up the maps fast enough in order to control this error. This is the way it goes, the proof. I'm not going into more technical things because that will be maybe trivial for the people in dynamical system, or not so trivial for the dynamical system, but certainly. But we have a preprint. You find a preprint on archive with all the details. Let me conclude this, say something about entropy, because I said before that entropy is, we don't use entropy or relative entropy in the proof. We don't use any entropy bounds. So, as I said before, it's useless to prove hydrodynamic limits for the energy. But this could be part of the problem if it is not part of the solution. It's interesting to know, well, what happened to the entropy. What about the increase of microscopic entropy and macroscopic entropy under this limit, since there's no noise in the dynamics? Let me state it in this way. So we have a density, rho star, of stationary measure. These are the stationary measure of the maps. And then we have the invariant Gibbs density at temperature beta -1 for the particles, position and velocity. And now you can assume that you start, you see, if you take nu n qp multiplied by rho star n d theta, you have an equilibrium measure for the dynamics. And now you start with something that has a density respect to the equilibrium measure. That's called this density G0 qp theta. So I was to start with an initial distribution defined this way. It's non-equilibrium, but as absolutely continuous respect to the equilibrium distribution of this dynamics. And you start that as a finite entropy. Entropy is a sense that the relative entropy of the mu n respect to the initial to the equilibrium measure. Yes, this should be nu qp. And in fact, I should put, I'm sorry, this should be just the equilibrium measure there, not nu pq, but the one on that's in theta. This should be also the integration in theta with G star. And typically you have to assume that this is bounded by constant times n. This is a deterministic dynamics. In deterministic dynamics, you let evolve the entropy, and there is no entropy production. The entropy you have at time 0, you will have at time t. It's a stochastic. In stochastic dynamics, relative entropy respect to the equilibrium distribution, the stationary distribution, will be higher, and it can compute the time derivative. But if in a completely deterministic dynamics, it's just entropy is constant. Let's lose some information. So I just integrate at time t the distribution, the density at time t. I integrate with respect to theta. So I don't want to look now at the position at the angles theta. I integrate on that. So I lose some information, and I can consider the relative entropy respect to the equilibrium measure. of the particles with respect to the Gibbs measure, and how does it evolve? Well, now I lost some information, so I should maybe see the entropy changing in time. And so this is the quantity. So you take the time derivative and you get a complicated expression. In fact, the time derivative is not zero now, but I cannot see, it's not clear that it's negative, or it's positive anyway. You should get somehow this decrease, and it doesn't decrease. There will be, there's no particular reason that in this time scale, I'm fixed on a microscopic level, there is an increase of entropy. There's no possible sign. There's no reason why it should be negative. I couldn't find any, but this should be related instead to the same entropy production of the stochastic dynamics. The stochastic dynamics, as you compute the change of entropy, and you get this Fisher information that is all caused by the stochastic term of the stochastic dynamics, and this is negative. So there is a decrease of the relative entropy with respect to equilibrium, like you have always for Markov processes, and one should wonder that maybe in the scaling limit, the marginal entropy, the time derivative, the entropy production of the deterministic dynamics should be somehow close and get assigned. I don't have a proof for this, but I conjecture this should be true, and we should see this entropy production in terms should be similar in the diffusive limit to the entropy production of the stochastic dynamics. Okay, so to conclude, what are the possible developments? We worked for 20, 30 years. I'm too old even to recollect this, with a lot of dynamics where we put conservative noise of energy of other quantities. In principle, we can try to avoid all those problems to put instead of conservative noise some similar chaotic fast perturbation. For example, this is in the case of the compressible Euler system of equation that my old work with Varadhan and Yao in 91, or in a lattice case, a paper with Nadine Even, where we do hyperbolic scaling, we obtain a compressible Euler equation, at least in the smooth regime, but we put there conservation, noise that conserve momentum, conserve energy, conserve volume, and so on. So we have the three conserved quantities. Will be interesting to, and this will be nonlinear. Possible to do things for nonlinear case because we are in hyperbolic scaling. There are no non-gradient problems arising. And I think should be possible with this technique to obtain the compressible equation from a completely deterministic dynamics with this type of noise. For the other work that I've done with Makiko Sasada 22 years ago, I think, or more, non-gradient dynamics with Green-Kubo diffusion. This is equilibrium fluctuation for the energy diffusion. The equilibrium fluctuation, this will prove us for an harmonic interaction, but we put a lot of noise on position velocity. I think this noise also could be substituted with some chaotic perturbation. When you study the equilibrium fluctuation, you don't have to use any entropy estimate. You are in equilibrium. It's just you have to show that the fluctuation converge to some infinite dimensional Roste-Uhlenbeck process, and you don't need. Then there has been work in the super diffusive case where you take a fractional evolution of the energy, and this is also work with Milton and Thomas some time ago. Even there, I think one can put, there is also done in one dimension, and pin case in one dimension when you conserve also momentum and volume. And then heat equation is not valid anymore. You have to look at the shorter time scale, and you get the fractional heat equation. I think also this fractional heat equation could be obtained using this conservative chaotic maps, and so on. Okay, so I finish here. Thank you very much. I think I stayed within the time. If there are questions, there's some time for questions.
Yes, you did. Thank you very much, Stefano. Are there any questions? You better go ahead.
I don't hear anything. Can you hear me?
Yeah.
Yeah. Yes. Okay. Yes, I was wondering. For your chaotic perturbation, you're considering a discrete time dynamical system. Is it something important, or could you consider a continuous time chaotic dynamical system?
Yeah, I think can be done. For example, you could put at each particle, you can use this flow negative curvature, and you have similar results. Then, of course, you have to adapt things. Nothing works by itself, but I believe associating dynamics in negative curvature, which are mixing, ergodic, and so on, and exponentially mixing, they should work. At least Carlangelo, which is expert on this, told me that should work. I will need his help to make it work. I'm not expert on that. That's in fact what he used in the paper with Dolgopiat to prove from a system of weakly interacting to prove that they converge to a Gies-Landau type of evolution. But all those results were for n finite. This is the first time in which this technique are used uniformly to obtain a result when the number of particles goes to infinity.
Thank you. I had a second question about the time scale separation. So for your proof, you need like A larger than 6. So I guess this means that the speed of the perturbation is at least n to the 8.
Yeah. At least it's not log.
Yeah. Okay. For the result to not for the proof, but for the result to hold, do you think you need a strong separation, or just a time scale that goes much faster than n2 is sufficient?
I believe any time scale fast will bring the same result. The result will be different without speeding up the map. I think without speeding up the map at all, so basically the map is acting the same time scale as the microscopic dynamics, I think the heat equation should be still true, but the diffusivity will be different. But we have no approach to that.
Thank you.
I have a question. Stefano, maybe it's a very naive question. This small intervals. Yes, can you hear me?
Yes,
more or less.
More or less, maybe close. And now?
Yeah, better.
Okay. These small intervals H, where you have a equilibrium, but the parameters Q and P does not move too fast. Do you interpret that as a quasi-statical transformation, or just as a technical aspect?
No, you see, there are 3 time scales here. So it's not quasi-static, because in the sense that this H, yes, in the scale H, particles don't really move. They move very, very little. But the maps are moved a lot already.
Okay.
So quasi-static will be different. Quasi-static is beat the result, say, but which you obtain from here because somehow you have uniformity in time. Where is it? Let me go back to the result. You see, what we call quasi-static scale is this one with beta. This means we go beyond beyond the time scale, the diffuse time scale, then you get a global equilibrium. Quasi-static means that things move globally. Eventually, if you have some boundary condition that change in that time scale, you will see things changing in this global state. That's what I mean quasi-static, yes. But this is different somehow.
Thanks.
I saw Milton raising his hand. No.
Any other question? Okay, so if not, let us thank Stefano for a very nice talk.
Thank you very much. It was a pleasure.
We'll see each other next week.
Okay, thank you.
Thanks, Stefano.
Bye.
Grazie.
Bye.